Hey guys, welcome to our sixth lecture. It's my pleasure to solve an example for you about first law and energy analysis. This is our second lecture about this topic. So let me go to the blackboard and then show which example I'm gonna talk about. So this is the second one, which is a combination, a combined question of two devices, a motor and a pump. And so, as always, please keep this example in front of you on your screen, because meanwhile I'm gonna refer to some information on this on the text. So, as always, in the beginning, let me read the whole example for you because we need to imagine what story, and we need to keep in mind that exactly what is going on. The question says an oil pump is drawing 44 kilowatt of electric power while pumping oil with the density of 860 kilogram per meters cube at a rate of 0.1 meters cube per second. Okay. The inlet and outlet diameters of the pipe are 8 and 12 centimeters respectively. If the pressure rise of the oil in the pump is measured to be 500 kilopascal and the motor efficiency is 90%, determine the mechanical efficiency of the power of the pump. I'm sorry. So this is our second example. As always, we need to determine our system in the beginning to clarify exactly what material, what portion of this figure or the story we're going to talk about, right? To specify the boundaries, the energy coming in, leaving the system, the mass flow rate, efficiency, and all this stuff. So we need to exactly know what is our system. So in the beginning, in the first site, we realize that we have, let me write it in this way. We have a combined system which consists of a motor and a pump. Okay. And the question is, mechanical efficiency of the pump. Okay. In this type of questions that we deal with a number of devices that are coupled together and they convert different types of energies, like for example here the motor converts electrical energy to mechanical energy, which is the shaft work, and then the pump receives this energy, this shaft work, and applies that energy to some sort of potential energy, which is supplied to the flow of the fluid, right? So we have two devices that are coupled, and the overall input is electrical energy, and the overall output is the potential energy in the fluid, like pressure or like height, like higher levels, I mean. Anyway, so let me put a note to help you that it says in combined systems, you need to separate separate se sorry, oh my god, separate individual subsystems, which here the subsystems are either the motor or or the pump, right? These are subsystems. Well, excuse me for a second. Okay. So in these combined systems, it's better to draw, to start with, the block diagram. So what is the block diagram? The block diagram is a simple figure that illustrates the inlets and outlets of like energy and power and everything. And we need to keep this in front of our eyes because it helps us to digest or like investigate the solution and like the procedure, easily, right? So let me show you. Let me tell you what do I mean by that. So as I told you before, the overall input is this energy coming in. I'm gonna call this E dot sub 1. Once again, E stands for energy and E dot means power. The dot means per time, energy per time, which is power. Okay, and then I have this output of this motor, which is called E dot 2, and then I have the overall output of the pump supplied to the flow, to the fluid, which I'm gonna call that E dot 3. Okay, so the summary of or definition of all these E dots would be, the first one is E dot 1, right? This is the electrical power, just the current of electrons, right? And that is the motor input. So we give this energy to the motor, which is, so in the question it says E dot 1 is, oh my god, where is it? Okay, it says E dot 1 is 44 kilovolts, right? So what does motor do? So the motor converts the electrical power to like mechanical power or kinetic power, to mechanical power, right? Which is given and supplied to, so the mechanical power is here is E dot 2, right? So the motor, it converts the electrical power, E dot in, to mechanical power, which is E dot 2. And in another word, it's called shaft power, right? So in this In the example, you can see like here, this kind of blue arrow, the curved arrow, it says it's like the shaft power that's coming out of the motor and going into the pump. And then, so let me continue defining these parameters. And E dot 2 is the shaft power, or like shaft work, and that is the pump input, or at the same time it's the motor output. And we don't know how much it is. It doesn't say in the question. So the pump here converts this mechanical power converts to potential power. Right? It's like potential power in the, or let me call this potential power supplied to the fluid flow, right? It's like, for example, pressure. Okay. Well, so on the other side I have E dot 3, which is that potential power supply to the fluid flow, which is the pump output. Okay, great. Now if you take a look at the lecture note number 5, pages 8, 9, and 10, then you'll be familiar with the definition of efficiencies for turbine and pump, and the other side generator and motor. Well, then if you come back here, you can probably go there, check it out, and then come back. So the motor efficiency is defined as eta, motor, which is mechanical power output. So efficiency is simply defined as the output of your system over the input of your system. Here the subsystem is motor, and the output of the motor is the mechanical power. The input is the electrical power. So divided by electrical power input. It's easy and simple. Okay, and according to our block diagram as I defined before, for the motor here I have E dot 2 as the output and E dot 1 as the input, which means that here I need to put E dot 2 in the numerator and E dot 1 on the denominator, right? And it's given that the eta of the motor is 90%. It's mentioned in the example. Therefore, 0.9 equals E dot 2, which we don't know, and we're going to solve for this right now, and E dot 1, which was 44 kilowatts. So E dot out 2 or out would be 39.6 kilowatt. So keep this in mind because we're gonna use this in future. Now we know, once again, let's go back to our block diagram. Now we know everything about E dot in, E dot 1 and E dot out, correct? And now we can switch to the second subsystem, which is the pump. So far we've been talking about the motor. Now we can switch to the pump. And here's a question, that why did I start with the motor? Because it always depends on what is provided or mentioned in the question. Sometimes the question might start with like E dot 3, and you need to go first and solve E dot 2 according to all the input and output on the pump. Then you can go like backward. Now you can go to the second, or like the first subsystem, which was the motor. You have E dot out and then 2, and then you can solve for E dot 1. So like in general, it depends on how this question is asking us. In this one, it is started with the input of the motor and the efficiency of the motor. So we can solve for E dot out, then we can continue to the second subsystem, which is the pump, and then solve for the efficiency and the output and everything. So now we can move to analyze the fluid kinetics, which is like velocity, pump and stuff, inside the pump, pressure and stuff inside the pump. Or I can like say here like mechanics as well. Anyway, so now we need to define a new system, right? So here is like second subsystem, okay, which is the pump. So the second subsystem is the pump, but I'm not going to talk about the pump physically. I'm going to talk about whatever is inside the pump. So I'd call that the pump case content, right? Which is the water flow. So I need to draw my system right now. But before I draw the system, I would like to mention that this subsystem is a new one, because we're talking about a flow. So please be careful that so far we've been like talking about just the closed systems, which is a certain or like a specific amount of mass, and that's it. We're gonna stay with this mass for the rest of the question. But here we're talking about a flow. So new mass, new water is coming into the pump. They get pressurized and they leave the pump, and this story goes on, right? So we have a flow, which means that we need to be careful that we have a control. Let me write this in red because this is so important. We have a control volume, right? Remember that I mentioned before, we have two different systems: control mass, control volume. Control mass is, as I told you right now, it's like just a specific piece of mass, and we're going to stick with it and just talk about that particular molecules. But in control volume, if I give you an example, like for an example, it's like if you hold your hands like around your eyes and just don't move your head, just look in front of you, and imagine that these molecules are coming into the domain that you can watch, and they leave the domain, right? So you are talking about the boundary around your hands. That is the volume. That is the control volume that you are focused on. You don't care about the mass, because the mass will leave your system eventually, right? They come and then they leave. But then the volume is fixed. The domain that you are focusing at is fixed. It's just around your hands. So it's a control volume. And also, since we're dealing with a flow, so the boundaries that we define, some of them are real, like the palm case, some are not, some are imaginary. And in most of the cases, the imaginary boundaries are the inlet and outlet of your system. So please be careful that we have imaginary boundaries. You'll see in next lectures that we're going to talk about properties of pure substances. In those examples, we will deal with just piston cylinder devices. It's just like real case, real cylinder and the piston. So the content is just a mass. There is no opening, no inlet, no outlet. The mass is like trapped. The mass is trapped there. It cannot leave. So the mass is conserved. I mean, like in both cases, the mass is conserved. But there, in that example, is just the same mass. The mass doesn't go anywhere. Anyway. So now I want to draw the system for you, right? So these two straight lines are the case. So they're like kind of real. It's like a metal case. And then I have these dashed lines which indicate my imaginary boundaries, right? So I have this inlet that is a combination of mass, and mass carries energy, right? And also in the outlet, I have this imaginary boundary that it carries the mass going out and energy as well, right? And also, so again, this system is the content of the pump case, right? Which is the flow, which is just the water molecules. And we know that the blades of the pump, they do work on this flow, and they kind of push it forward, and they increase the pressure, right? So we have this input, this energy input that is coming from the blades, coming from the shaft or pump in general, and it's supplied to the molecules of the water. So I have another inlet, which is this energy, right? And as I defined it in advance here before, I called it E dot 3, which E dot 3 was the potential power pump output. See, pump converts mechanical power to this potential power supplied to the fluid flow. This is what is coming into my subsystem here, right? So this is my subsystem, okay? And I called that before E dot sub 3. That's all the energies that I have. Let me write the other parameters here. I'll call point A and point B as inlet and outlet. So point A is pump inlet, and point B likewise would be pump outlet, right? So in parameters, I would have m dot a here coming in and m dot b going out, and similarly a dot a and e dot b. Energy coming in, mechanical energy coming in, carried by the mass, and E dot B, mechanical energy leaving the subsystem, carried by the mass again. And once again, let me write this for you. Mention that E dot, just to keep this in front of our eyes, that E dot 3 was the power supplied to the system here. By system I mean the subsystem, right? It's just the same thing. To the system, which was the flow, but the flow, I mean the portion of flow that is like around our hands. Remember that example? That part of flow, not the rest of it, not the upstream, not the downstream, just a piece of flow. It's not mass, it's just flow. From, I mean, like, it's not a particular mass. From the pump. So pump does work on the flow, right? Simple. Now we need to go to first law. According to the first law of thermodynamics, we know that E dot coming in minus E dot going out equals the change in internal energy of our system, right? Also, we know that this example is a steady state example in time, which means there's no change in internal energy overall. So dE over dt would be 0. It's steady. Okay. So if I substitute all these inlet and outlets that I define here in my system, I would have E dot A, the energy carried by mass, inlet, plus E dot 3, sorry, it's not the energy, the power. So again, the power carried by mass coming into the system, plus the power supplied to the system from the pump equals whatever is going out, E dot B, the power carried by the mass out of the system. And according to the equations that I gave you before on the notes, I can substitute the overall mechanical energy of this E dot sub A and E dot sub B here. So I would have this is the famous equation, velocity square over 2 plus g za plus likewise here at point B, outlet. And in this, at this point, we need to assume some, like, to have some assumptions. That first one is, it says that point A and B were picked right at the inlet or at the pump inlet and outlet respectively, right? So, and we know that the pump size is relatively small. So what does that mean? It means that if you compare point A and point 2 altitude, these heights are the same, just the inlet and outlet. If you can see it on this picture. Here, this point and this point, like that is negligible. This height is like a couple of centimeters or inches. That's fine. We can just ignore that. So it means the change in height is negligible. So ZA equals ZB. And by conservation of mass, we know that m dot A equals m dot B, right? Which is like m dot, just m dot. There's no leakage. There's no mass doesn't leave this. The only inlet is A and the only outlet is B. There's no other outlets for the mass, right? Which means that here I can cancel these two terms because these are the same, and these two coefficients behind the parentheses are the same, so I can safely cancel these parameters out. Anyway, so I'll end up with, and I can take them to the one side, those parentheses to the one side, then I'll end up with E dot 3 equals m dot times PA minus PB, or sorry, PB minus PA divided by rho plus velocity squares difference divided by 2. So now we found E dot 3. Once again, if you check the block diagram, we can find the E dot 3. And if we divide E dot 3 by E dot 2, then we can find the question. The question asks for mechanical efficiency of the pump, outlet divided by inlet, power outlet divided by power inlet. So all we need to do is just to find E dot 3. We have previously found E dot 2. Where is it? Here, see? And that's it. But we need to pay attention that the difference between the pressures and the density are given. These are given. It's solved. But we do not know anything about the velocities. So the velocities are unknown. Right? So at this point, we need to pause and we need to solve for velocities first, then we can put them there in that equation and solve for E dot 3. So here we need to solve for the velocities, right? And by velocities I mean A and B, at the inlet and at the outlet, VA and VB, their velocities. So if you take a look at this example, it says the inlet and outlet diameters of the pipe are 8 and 12 centimeters. This information is about the geometry. And on the other side, a couple of words before, we have that the oil flow rate is 0.1 meters cubed per second. So that is the volumetric flow rate. And we know the relation between the volumetric flow rate and area and the velocity, which was that V dot equals A area times the velocity. This is what we know, right? So we can easily just substitute this V dot volumetric flow rate and A and just solve for velocity. So this is volumetric flow rate. By volumetric, I mean that the unit is in meters cube, length cube. And I'm sorry, I'm gonna finish this soon. So I have the conservation of mass, dun, 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 and in compressible assumption, right? Which gives me that the volumetric flow rate at the inlet equals the volume. So on the other case, it's like m dot A equals m dot B, therefore rho v dot A equals rho v dot B. This is sub A, this is sub B. The densities are the same, therefore v dot A equals v dot B. Okay, now I need to solve for this equation 2 times and just plug in all the properties about the geometry, the area at the inlet and at the outlet. And I know that v dot, which is these guys, it is 0.1 meters cube per second. So I know that v dot A equals A v A. They're both, so A v A. So 0.1 meters cube per second equals pi over 4. The diameter at point 8, which is the inlet, is 8 centimeter square times the velocity. So velocity would be 19.9 meter per second. And once again, let's solve this equation for at point B, the outlet. But the volumetric flow rate is still the same as I told you before. So, and the outlet is 12 centimeter, the diameter is 12 centimeter square. So this is the velocity, therefore VB equals 8.84 meter per second. Great. We're about to finish. And I know that m dot equals rho v dot. So once again, if I check back my equation up there, I can say that, okay, m dot I know, and then substitute everything there, right? So I'm gonna solve this equation, which is rho here. This is instead of m dot times the change in pressure divided by velocity plus the difference between velocity squares at the inlet and outlet divided by 2, and it's given that delta P is 500 kPa, kilopascal. Therefore, the density is given 860 kilogram per meters cube in the text. Volumetric flow rate is 0.1 meters cube per second. I'm sorry. So divided by the change in pressure should be in SI unit, which is 500,000 Pascal, divided by the density. As I mentioned before, this is the density plus at the outlet velocity 8.84 square minus 19.9 square, and the unit is meter square because everything now is squared, divided by 2. So E dot 3 is 36.3, right? Conservation here, I forgot to tell you that you can check this page of note number 3, page 4. And based on the pages about efficiency, we know that the efficiency of the pump is defined as mechanical energy increase of the fluid divided by mechanical energy input, which was shaft work, in other words. Shaft power, sorry, or work, they're the same. Oh no, power, yeah. So the inlet of the pump divided, the outlet, the energy outlet of the pump, E dot 3 divided by E dot 2. E dot 3 divided by E dot 2. So the efficiency for our pump is, it was so long, I'm sorry, 36.3 kilowatt divided by 39.3 kilowatt, which is 0.98. So is 91.8%. And there's just one little tiny more thing to mention, that the overall is just an extra thing. Okay, the overall efficiency of the motor pump system is defined as, so eta MP equals eta M times P, which is 0.9 times, for pump it was 0.918. That would be, sometimes they ask about, now what is the overall efficiency? It means if I give you, so my whole system here, the whole system is the combination of these two, motor and pump, right? So the overall input is here. This is the overall input and this is the overall output. So if I divide the overall output by the overall input, I can get the efficiency of my the whole system, which is this guy. Thank you for watching this lecture. It was my pleasure to describe and solve this example for you.